Hello everyone, and nice to see all of you here today. So, JCAF community is on air, and we continue our series of workshops devoted to different technical topics. So, for today, I see that there were quite a lot of registrations on the Weir community platform, so you're truly interested in the topic which we're going to discuss. So, let's save some time for our speaker and let me introduce you to him. So, Yevgen Baranowski, lead software engineer at EPAM. And today, Yevgen will tell you about the brand new version of JDK, the thing which actually is truly important, not just by the fact that this is the regular update, but also because this is the last update before the LTS version. So this is something which we possibly might need to live longer with in terms of the new features, which might become a part of the LTS version as well. So it's definitely important to understand what exactly waits us there. And today we will have the workshop format with some examples, with some interesting code parts. So do not be afraid that you might miss something. We will share both the presentation and the code on the Weir community platform. And in case if you have any questions, you can post them into our YouTube chat as well as on the Weir community platform. By the way, guys, please feel free to I see you have already started to to see us. Can anyone share link? Oh, okay. So, yep. Anastasia, could you help the chat with the recording? So our like miracle helper from the background, we will help you with the link to the stream. So I hope that this will be resolved soon. In case if you experience any issues, yep, thank you guys. So I see that the link has already been posted into chat. Looking forward to see all the participants in our YouTube stream or on the Weir community platform. Don't hesitate to use both these platforms for your questions. We will have a dedicated slots for answering and asking. So also, I would like to pay your attention. Please stay with us till the end of this session, if possible, or at least please do not forget to return back to the page of the event on the Weir community platform, because we will place the survey at the very end of the session and in the Weir community platform chat to ask you about the further topics which might be interesting for you. But as of now, let's begin from the very beginning. And Yevgen, the floor is yours.
Okay, thank you for introduction, Tatiana. Hello, everyone. As it has been already mentioned, our today's topic is about JDK 24 and all the features and APIs that come with it. And before we start, a couple of words about myself. So I've been a lead software engineer at PAM Systems with some years of experience under the belt. I worked in different business domains. I practice both hands-on engineering and architecture. Technology-wise, I specialize in Java, backend, cloud, data engineering, and NoSQL. And in spare time, I experiment with knowledge management and enjoy video games. And about our today's agenda, we'll have 4 major sections. The first will be some sort of light warm-up, where we will mention some small things that might be not very useful day-to-day, but might be important in specific situations. So it's good just to know about them. The second section will be dedicated to the APIs that have been finalized in JDK 24. There we will have some examples that I'll demonstrate in my IDE, and later you might dive deeper if you want by following the link with the code samples that we will share at the end of the presentation. The same goes for the third section. It will be with some examples as well, but it will be about some features that might change in the future. And we will conclude our today's meeting with some words about what is going on inside the JVM itself. So not all improvements might be about the code that we write day to day, but it might be also about performance, ergonomics, and tools. So this will be about that. And without any further ado, let's get started with the first section. Honorable mentions, small but probably useful things. The first GP is about the restriction of Java native interface, and that's because interaction with native code directly might lead to some unexpected behavior in JVM, including crashes. So the developers of the platform decided that it's time to give the decision about whether to allow this feature or not to those who actually manage the runtime environment for the application, not those who write the code for it. And the first step is to introduce a warning, but in the future, uh, this feature will be disabled by default, so it will have to be enabled explicitly using the special flag. Next, all we know that quantum computing is developing steadily, so there might be some new security breaches related to that, and the Java prepares for those probabilities by introducing some security features, security APIs that address possible attacks in this direction. Quite close topic to that is about key derivation function API. It's just a preview in JDK 24 still, but it might be useful for those who develop new cryptographic libraries, for example, and frameworks, security frameworks. Next, we have removal of Windows 32 port. It has been deprecated since JDK 21, and it's time to clean up some code because this port is probably not necessary anymore. The next thing is about the removal of Security Manager, the good old friend that has been with us since pretty much the first version of Java. And now it's replaced with more modern features, which are already included in runtimes like OS, container runtimes, etc. And they have a stronger feature set, more modern APIs, and are easier to use. So this thing is no more as of JDK 24. Next, some toolkit improvement related to how we can build custom Java runtime images. And now it's not mandatory to use JMods for this, which allows to cut down the image size by around 25%, which is a nice boost for those who are looking into optimization of infrastructure costs. The next thing is about another well-known topic, unsafe. The JDK developers continue to gradually go away from it in favor of more modern APIs, including var handle, which is with us, I believe, since Java 8 at least. Then we have foreign function and memory API, which is a more modern replacement to Java native interface. And it's recommended to try to port any specific features that came from unsafe previously to those APIs. And please note that in JDK 26, those deprecated methods will be unavailable completely. Next, we have a deprecation of 32-bit port for other platforms other than Windows. According to usage statistics, as I understand, this port is almost gone. So it's another opportunity to clean up some code and improve maintainability of JDK code base. And let's finalize with a couple of other very small changes, but which might be useful in some situations nevertheless. First of all, it's about new GFR events, which is good for profiling. Also, we have some API improvements, minor additions to I/O, cryptography, and string API. And if you are interested in more details on those topics, you may follow the link provided on this slide. Okay, so that was our warm-up, and now let's jump into some real things, which will be about finalized APIs. And the first feature that we have for today is about stream gatherers. So everyone know and hopefully love the stream API that was introduced along with functional programming features into JDK. But it's time to expand it a little bit. And the reason for that is it's sometimes necessary to heavily customize the pipeline that is built with streams. And the existing collectors API might not be enough to cover all the cases, especially from the efficiency standpoint. And to understand the motivation better, let's have a look at one example. So let's switch to my IDE. Please confirm that you can see my project, my code. Tatiana, can you see it?
Muted. Yep, we do. Everything is fine. Thanks.
Great. And let's have a look at a couple of simple examples. So let's suppose we need to build a simple calculation, which is about calculating the average over a set of sliding windows, and the sliding windows are calculated based on a stream of numbers. All the three implementations here provide basically the same functionality, but they are slightly different in terms of implementation details. The first one is the most straightforward, is based on plain Java code and implemented with just a for loop. So we iterate over our number stream, calculate the current window, calculate the average for it, and add the result to the output. So it's pretty straightforward, but unfortunately, it's not very reusable, and it's quite explicit. So not much declarativeness here. And the next step to improve, at least in terms of declarativity and reusability, is to go with the streams API. And here we have the usual collector-based approach, where we declare the aggregation that we want to do, how we act on this aggregation, and after that, we have to close the stream because, as you might know, the collect call is a terminal operator in the streams API. And for this reason, since we have a set of sliding windows as the output, we have to create another stream, and only then we are able to separately calculate average or probably some other metrics. So it's more declarative, but unfortunately, this part where we have to accumulate the whole collection result in memory is not very efficient. And I'll demonstrate how bad it may end a little bit later.
Yep, just a side note, could you make fonts a bit wider? So guys in the chat mentioned that it would be like easier to follow you. So could you make the font a bit bigger, possibly?
How much?
Oh, yep. Just a tiny bit more, I think. Yep. I think that's better. Thanks.
Okay, thank you. All right, and the third implementation is based on the new Gatherer API, which introduces basically the same functionality as with collectors, but right in the middle of the stream. So it's not a terminal operation, and because of that, it's possible to continue appending other operations to the stream without accumulating the intermediate results. internally. So if we look at the collector-based implementation, as I've already mentioned, we have to accumulate all the windows in memory. And this is the major concern for us in case we process a big stream of numbers, which contains thousands, millions, or even more elements. With the Gather API, we have very similar structure in terms of what we do. So we declare, again, some sort of aggregation object. Then we declare how we act upon it when another item from the stream arrives. And then we have the last step that concludes our aggregation. And this implementation is pretty similar to what we had with collectors, but it holds just one window at a time. So it's far more efficient in terms of memory consumption. And the major change in the API is that it takes a special object called downstream, which is basically the input for what comes after the gather operation. And it's up to the gathering accumulator implementation to decide whether to push new items or not, whether to update state or not, and even and it's also able to decide whether to process any further items as well. Sorry. So if we look back at the test, we can see that the Lambda function, which defines how we act upon our accumulator, returns a Boolean, which is an indicator of whether or not we want to take any new items. So in case we return false, the upstream is closed and the operation ends completely. Okay, and if we look at the entire, the full setup of hypothetical gatherer, we have quite a few moving parts here. So first of all, we have the input stream. Every item from the input stream, possibly in parallel in multiple threads in case the stream is parallel, is passed to the integrator. And the integrator in our example was the accumulation logic. Optionally, we may have an initializer which creates the initial state for the aggregator. And then we have an optional function which is able to combine the results of multiple parallel streams. And also we saw the third lambda, which was so-called finisher. It defines how to extract the final result from our intermediate results held by the integrator and combined by the combiner. And of course, as you might have guessed, the windowing aggregation and similar logic is pretty common. So JDK comes with quite a few out-of-box implementations for gatherers, which include sliding windows, fixed windows. Also, it's able to fold stream. So basically, it sort of collector which but instead of returning a plain number, it returns a stream of one element. Also, we have a multi-threaded map version. To be honest, not sure why we might need this. Probably someone have a better idea of that. And finally, we have the scan gatherer, which is able to do something pretty similar to fold, but instead of outputting just one final element, it outputs all the intermediate results. And as I've already mentioned, I have a benchmark, GMH benchmark, which demonstrates what bad things can happen if we use collectors for calculations like with large streams. And for that, we set a limit of 64 megabytes of heap size for this experiment. And we measure how the collector is able to compete against gatherer-based implementation on a number stream containing 1 million elements. And to save some time, let's show the results. The result actually contains just the output for the gatherer, because if you look at the GMH logs during the execution, the collector-based implementation just fails with out of memory. So that's why we might want to consider switching to gatherers in some situations over collectors. So that was the first feature. The next feature, finalized feature, is a so-called class file API. So what is it about? It's about bytecode manipulation. And as all we know, there are already pre-existing libraries, pretty mature ones like ASM, for example. So it's heavily used by such frameworks like Spring Framework for aspect-oriented programming and similar things. Also, bytecode manipulation is used by developers of JVM-based languages like Clojure, Scala, Kotlin, etc. So it's pretty an important feature. But nevertheless, ASM and other libraries like that are third-party libraries, so they are not part of JDK, and sometimes it might take some effort and time resources to keep up with the JDK changes. And because of that, it would be great to have actually something which is part of JDK out of box. And the class file API is actually the solution. And let's have a look at an example how it can help us in case we need to customize our bytecode. So this will be quite an advanced example. I will not focus too much on the details. I'll just point out the key milestones in it, and you might follow the code later on if you want to get into details. So this example is about creating a proxy which takes a concrete class and adds login statements at the beginning of every public method declared by the service. So in this case, we have a simple calculator service which have a very basic method for adding two numbers, and it just adds a log statement with the method name and the arguments to the log. So if we look at the output, sorry, logger is mocked, so we will not see anything. So we will just have to trust the assertions that we have here with GUnit. And if we look at the implementation, it's quite an involved one, actually. I will not focus on all the details, just let's have a look at what's going on. So first of all, we have some validations regarding the class that is passed to us for proxy, because we are not able to proxy an interface because we need some business logic to log around. Then we take the declared constructor, public constructor, with no arguments from the class for simplicity. In more advanced setups, you would like to duplicate other constructors as well. Sorry, and then we create the structure which we'll use for holding the bytecode before outputting it to a class loader. Later on, we get the bytecode and pass it to the class loader. And the most interesting part is about what is going on with the class file itself. So first of all, we create a class descriptor, which is basically package name plus simple name. In this case, we take the input class name and append a fixed suffix to it, just like, for example, cglib does. Then we construct the top level. So first of all, compared to such libraries as ISM, the class file API tries to use the most modern features of Java, including Lambda functions, and structures its API so that the likelihood of subtle mistakes is minimal. In ISM, on the contrary, there is a lot of space for subtle mistakes because it's more low level and less explicit sometimes. And if we look inside, the top level structure that is derived from the file is class itself, of course. So we build a descriptor for the class, then we add a field to it, then we add a constructor to it, and finally we go through all the declared public methods of the input class, select ones which are available for proxying because we can't do anything with final methods, for example, and then we create a proxy for each method. The overall code is pretty complicated, so let's have a look at the most simple example, for example, how we can add a field. So we have a class descriptor of the logger class, slf4j. Then we declare the name of the field and define the flags that we want to have with it. In this case, this is private and final. Defining the constructor is more complicated because we have to add some instructions here, and basically this begins with the invocation of the super constructor, then an if-else statement which validates that the logger field passed to the constructor is not null, and throw an exception if it's null. And finally, we initialize the logger field and return nothing. So you might go into more details if you want later, but let's not dive into too much details right now. Let's go on to the next section, but before that, probably we have some interesting questions regarding the part that we went through so far.
Actually, we do. There was a question, I think, during the gatherers section.
Okay.
How would the plain Java implementation handle it instead of using all that streaming pile? So in runtime, how it would be handled under the hood?
Well, I believe I demonstrated that already, but let's go back to the example. Okay.
So
we
this
have...
is, if I got it right, more about how it works. Yep, from the inside, and this is exactly what you had demonstrated, or?
Well, to be honest, I haven't had a look inside the implementation code, but pretty obviously we have. So basically, the implementation, I believe, follows the API structure that we have. So if we go back to the diagram that I've demonstrated, we have the integrator, and it's the thing that holds the potential state. In this case, we have the array that holds the elements for the current sliding window. And whenever a new item comes in, the Lambda function, the integrator function, is invoked. And in our case, it's translated to the add method, which puts the item to our array. And also, if the window is complete already, so it's of a necessary size, we push the window downstream. So our downstream in this case is a stream of windows, not just numbers. And basically that's it. So it's a collector which outputs not some aggregated object, but a stream of objects. And for that, we use the downstream API. I hope that this clarified a bit.
Yep. So the additional question here is, where is the comparison of runtimes of plain Java versus this gatherer? So I would like to ask possibly to clarify which exact comparison is meant. So just in terms of code or in terms of performance, the comparison might be in different directions. But I think
So
that this is about
the plain Java implementation would be just a for statement that iterates over our input stream, creates windows, and outputs an array of averages. I believe that's it.
So mainly, yes, this is how it would work in like earlier versions of Java, and in the versions of Java earlier than Streams API, almost kind of. Yep, I see that the Windows streamer.
So
Yeah,
in
great,
earlier
right.
versions of Java, to be safe on memory, you would use an iterator as an input and some sort of stream as an output. Something like that.
Okay, so I see the clarification in the chat. Can you provide the times comparison? So I mean the performance comparison, if I got it right, the execution time.
Well,
So
my GMH benchmark was aimed at demonstrating memory unsafety of collectors in some situations. So the implementation based on collectors fails with out of memory. If you are interested, you may increase the memory limit and see the results for yourself after the presentation.
So, yep, guys, you will have the repo and you will be able to run these benchmarks yourself to see the difference between these code pieces. So I think that we will definitely share the links and you will have a chance to return back to the recording as well as to this part of the repo. And just one more question I would like to add is about the bytecode modification stuff. So what could be the real programming use case of bytecode modification?
Well, let's get back to the presentation, and the use cases include the development of JVM-based languages like Groovy, Scala, Kotlin, etc. Aspect-oriented programming, which is heavily used in such frameworks like Spring Framework, Spring Boot, Micronaut, etc. Instrumentation agents, which add such features as profiling, for example, and different developer tools, like, for example, leaf code reloading in Spring Framework or Quarkus.
Yep, so this is more about the service stuff, definitely not something about the
Yes, no, this is not
enterprise
about business
features.
logic.
Yep. So thank you very much. I think we can go to the next part, and all the questions which will be asked during it will be answered in between the next two sections.
Okay, so let's go ahead. And the next section will be about previewing and incubating APIs. So those features are not finalized yet and may change, especially those incubating. And the first one is already well known. It's structured concurrency. Unlike virtual threads, it's not finalized yet, but there were no major changes since JDK 23. So it's expected that structured concurrency will be finalized in the next long-term support version, namely 25. And just to recap, what is it about? It's about more ergonomic multi-threaded programming, which is quite common in business applications. And let's have a look at an example which demonstrates which issues we might encounter with the classic approach based on executors. So let's jump into some code and let's assume that we have a simple interface. Sorry. Here we go. So we have an invoice service which acts on customer data, order data, and some localization data in order to create an invoice, which is, for example, sent to the customer over email. And we have two implementation of this interface. The first one is based on the well-known executors. And here we have an executor service, 3 parallel tasks which are forked using it. So namely, we get data for the customer by ID, for service by ID, and for a template file based on the language, based on the locale. And
Yep,
then we have a bunch of...
interrupt you
Yes.
one more time. Sorry for that. Please do not hesitate to make the fonts even wider, so something like 30 points or so. I think this might work a bit better for the audience because I understand that you share quite a lot of interesting code, and it might be better to make it a bit bigger. So sorry for that reminder. Thank you. And yep, please go ahead.
Okay, so after we have our subtasks started, we need to basically join for them. And we have quite a lot of code lines dedicated just to exception handling. So in case we are talking about the first task, we need to check whether it failed or not. If it failed, we might want to save some resources and try to cancel the other two tasks in case they haven't completed yet, and then propagate the original exception upstream. And pretty much the same thing for the second and third task. So quite a lot of boilerplate code. And only in the end, we are able to invoke the template rendering logic, which takes all the data that we collected in parallel. And let's have a look at another implementation, which is based on the structured concurrency API. So it's quite a few lines shorter, and it's more structured, as the name of the API implies. So first of all, we declare the scope, which is sort of a context for our operations. It's possible to have nested scopes as well, as I'll show on a diagram after that. And here we have a pretty similar API in terms of how we fork parallel tasks. So it's just about supplying some Lambda functions with business logic. But then we have much less code related to exception handling and similar things. So we just invoke join call on the scope, and then we declare what we want to do in case any of the tasks failed. So in this case, we want to fail if any of the tasks failed. And then we really get to the results and invoke our business code. And if we look at the complete diagram of how this might be structured in more complicated cases, as I've already mentioned, we have the surrounding context called structured task scope. So it's the supervisor, and also it defines the policy of how to behave in case any of the tasks complete, any of the tasks fail, etc. There are a couple of basic implementations which will be most useful in day-to-day coding. So, which is already demonstrated in the example. And typically, you would have virtual threads as the workers which back your tasks. It's possible to use platform threads nevertheless, but I would say that this is not recommended because you are easily able to spawn hundreds or even thousands of subtasks, and this will surely deplete your platform thread pool very quickly. But with virtual threads, as we all know, this is much more efficient and much more easier to create threads without taking care about how to manage the underlying resources. And also, as I've already mentioned, it's possible to have nested task scopes, which allows us to organize our logic into tree-like structures where supervisors sit on top of supervisors. And what is it used for is actually in case our policy is fail always on any failure, the top level supervisor will always cancel anything that might be running in its child scopes before propagating the exception upstream. So this is quite useful and quite handful. And the last feature that I would like to mention in this overview of structured concurrency is about scoped values. So this is the alternative to thread locals, which is recommended for use with virtual threads. So as I've already mentioned, you are able to spawn a lot of virtual threads. And as we all know, thread locals are easy are a good source of memory leaks, I would say. So it's easy to forget to remove thread locals when they are not used anymore. And with virtual threads, having thousands of thread locals may easily overwhelm your heap memory. And with scoped values, this looks a little bit different. So let's have a look at another example. Sorry. At another example, this will be about how we might leverage scoped values for tracing. So we have a tracing context where we have our scoped value, a replacement for thread local, and its destiny is to hold the current trace ID. And we have a pretty simple API for getting the current trace and for executing some Lambda function while wrapping it into some sort of scoped value with the given value for trace ID. So with this construct, you are not able to forget to remove it after it's not used anymore, because you define all the logic that relies on the current value inside a Lambda function, and once the Lambda function completes, normally or abnormally, the scoped value will be cleaned up automatically. And you might look at the unit tests provided here, but let's probably have a look at some corner cases, more complicated ones. So this will be about the following. First of all, you must respect the fact that subtasks within a scope are not allowed to call each other directly. So the fork call on the scope returns the subtask handle, which is later used to retrieve the result. But it's not allowed to access this handle inside another task. You'll just get an exception. So this is what the test expects exactly. So this is the first pitfall. The second pitfall is about the fact that it's possible to use platform threads with structured concurrency. So when you create a structured task scope, you are able to provide the thread factory. And by default, it's a virtual thread factory. But it's possible to provide a platform threads factory, which is not a very wise decision, as I've already mentioned, because it's expected that there are a lot of parallel tasks, probably, and you might run out of your platform threads pretty easily with this approach. Then we have an example which demonstrates shutdown policy, but this is basically what we already saw in the first example. And I believe this is pretty much about the corner cases, the key pitfalls, the key facts that you might want to know about structured concurrency. The next feature is about flexible constructor bodies, which is kind of a simplification, especially in case we have to deal with extending some third-party code. Let's have a look at another example. So let's suppose we have some third-party library with a cache, namely the third-party cache, and let's assume that is able to provide us with runtime encryption, and it's configured with an algorithm. And on top of that, it's quite expensive to invoke this constructor. So in case we pass some bad algorithm, it will be initialized nevertheless, but we might not want to work with this algorithm because it's vulnerable to some attacks. And for that reason, we decide to develop our own secure cache, which extends the third-party solution, and it contains some set of production-proven algorithms that we trust. And we want to include this validation before invoking the super constructor. So first, here, idea, woke up finally, uh, before invoking the super constructor. And what's the point here is that previously it was not possible to have any statements before superconstructor at all. And now it's possible to do so as long as the code in the statements before the superconstructor doesn't have to do anything with the parent class fields. So you may use any static logic, like for example for validation, and also you are able to initialize the fields of the child class itself. So this might be pretty convenient in some cases. The next feature is even shorter and simpler because it's intended to make Java usage very lightweight in some cases, and it's about simple source files. And the problem that this feature tries to solve is is to smoothen the learning curve for Java newcomers. So, for example, in universities, not always it's possible to have an environment with a full-fledged IDE, or, for example, you might be on some travel and you want to write a bit of Java code, but you forgot to install your favorite IDE and you have just a JDK, GRE runtime. And previously, that prevented you from developing some code in Java. And now it's possible to bypass this limitation by writing your Java code as a single file of simplified format, which is great for educational purposes. And finally, it allows to include compilation as an implicit step instead of having to invoke the compiler by the developer. And let's have a look at an example how this might look like. I have an example where suppose we want to try the HTTP client built into the JDK since, I believe, Java 11, if I'm not wrong. And for that, we write a pretty simplified Java source file. First of all, we are able to import the whole module with the classes and the APIs related to HTTP client. And then we are not obliged to declare the top-level class. We just need to declare a simplified main method signature. It doesn't have to be static. It doesn't have to have any arguments at all. So it's a pretty simplified structure. And let's probably run the example. So this example, basically, what it does, it makes an invocation of the public Zen quote service, which provides quotes of the day for free. Let's run the thing. So as you may see the script, it just invokes the Java machine. It enables the preview feature because this is a preview feature, and it's supplied just with one source file, and it runs just well. So it returns us 200 status code and our requested quote. So a pretty useful thing for experimentation and education. So this is a little bit more explanation of this one. And the next preview feature is another small improvement, which is related to pattern matching and instance of statements. But this time it's focused on primitives. And to understand the benefits of these features better, let's have a look at another example. So suppose the simplest one will be probably, which one? So let's have a look at CPU classifier. So let's suppose we work with some infrastructure management code, and we want to have a service which is able to determine the optimal instance size based on the number of requested CPU cores. And here we see the already usual switch statement, but the cases in it are a little bit unusual. So first of all, it's able to match not a num, not a string, but a primitive. In this case, this is the number of CPU cores. And also it's enhanced with guard clauses, quite an exotic feature. Not sure how much used is it, but it's quite useful, as you might see. So we declare that in case the number of CPU cores is between 1 and 4, we choose small instance. In case this is 5 to 8, this is medium, and etc. And of course, we have the default clause. And the main improvement here is the ability to use number as the switch target. The next also a simple example is is about being able to use instance of with primitive types. So sometimes for some optimizations, for example, as we will see in the next example, we might want to know, for example, whether a larger number type is safe to be cast to a smaller number type. In this case, that's about double and byte. And a statement like that allows us to decide whether or not the actual value held in the double variable may be cast down to byte. And a more advanced example for that is as follows. So let's suppose we have some key value storage engine which provides APIs for storing bytes and doubles. And obviously, the byte-based API might be more cost efficient. But we want to store arbitrary data in it. And let's suppose we have an API which takes double parameters. So this is just a record with a key and double value, but we want to know whether or not it's safe to extract the value from the parameter, cast it down to byte, and use a more cost-efficient API call instead. And another feature which is demonstrated here is the ability to extract primitive values out of records. So it works with nested record patterns as well, as you see. And of course, we have a set of unit tests that verify this behavior. So you might, if you want, you might check that these all these features work just well. Okay, so that's about primitive patterns, and the last preview / incubating feature is about vector API. So vector API have been existing in JDK already for some versions. It's constantly improving, but it's still in incubation. Nevertheless, it's already used in some tools. For example, the JLlama project, which is an LLM port onto JVM, already uses the vector API to provide better efficiency on modern CPUs. And what modern CPUs provide to us is the ability to process multiple data points with a single instruction, so-called single instruction multiple data operators. And in some cases, just-in-time compilers in ordinary JVMs is already able to leverage this capability for some simpler code. So, for example, for plain loops, which iterate over numbers. But for more complicated logic, which is, for example, used in scientific calculations or machine learning, just-in-time compiler is not able to see that there are opportunities to leverage those instructions, and the resulting code is less efficient. Is not as efficient as we might want it to be. And the solution to this is to have a special API which leverages those low-level features directly. So we are able to somewhat declaratively tell JVM that we want to leverage more advanced CPU features. And of course, we have an example of this API. It's very simple. So it's some vector math, which, let me hide unnecessary things. So it's simple addition of two vectors A and B. And in plain Java, we would have just a plain loop. But as I've already mentioned, for more complicated calculations, a just-in-time compiler might not able to leverage SMID instructions. And in those cases, we might want to leverage one of the two styles of using vector API, one with masking and another without masking. So the major difference between the two is that with masking it's easier to write code somewhat. So it's easier to iterate over vectors, but it's less efficient because it might result in redundant operations. And more advanced version is to use no masking at all, but in this case, we are able to process just those parts of vectors which ideally fit inside the given CPU architecture. And the remainder of data which doesn't fit those data types has to be processed with another plain Java loop instead. And let's have a look at a JMH benchmark for that. So here we compare the three implementation, one with a plain Java loop, another with masking vector API, and yet another one without masking. And please note the fact that for the plain loop version, we have to specify special arguments so that just-in-time compiler doesn't do the optimization for us and doesn't leverage the SMID instructions underneath. So we are able to see more fair results. And let's have a look at what it might look like. So even for this simple operation of adding two vectors, given a data stream large enough, we see that the plain loop version performs worse than both vector-based implementations. And for more complicated logic, the difference will be a lot more pronounced. And the benefit of the vector API is actually that it's possible to chain operations. So for example, you are able to add, so ID, please help me, add, subtract, even add conditional logic, etc. So it's up to your imagination how you might use these features in production. Okay, and that was the second section. And now it's time for some questions before we wrap up our presentation with some JVM upgrades. Tatiana?
So, yep, we have the interesting question actually about the simplified form. Is it expected to be the norm even for enterprise professional applications, or is it only thought for educational purposes?
I would say that this might be more for educational purposes, and I wouldn't be surprised if this style of coding might be removed in further JDK versions because the vector API, as I've already mentioned, is incubating and might change substantially.
Not the vector API, but the simplified form of Java code. So which you mentioned about the function.
Yeah, so yeah. Yes, it's pure. It's more for the cases when you are in a limited environment with a limited toolkit. So you might not have your favorite IDE. You might not have access to such build tools as Gradle, for example. So you might have just a Java runtime environment and a text editor. And in this case, you are able to do some coding without having access to a compiler. And of course, this is especially useful for educational purposes. So for universities or for those who learn Java in their spare time, etc.
Actually, I do see a huge opportunity in this technology. So basically, the syntax is somehow similar to what we have in serverless computations. And this is like the scripting tiny piece of code which doesn't require too much libraries to be started, which might be as lightweight as possible. So I feel that some services like I don't know, AWS Lambda or Azure Functions might get huge benefit from being able to operate with this like simplified approach. But definitely, this is also about what's happening under the hood and how many additional infrastructure things should be set up to run this tiny piece of code. But in terms of the code style, this is something which looks exactly like the good way of writing some tiny pieces of code which might be run as serverless computations. So what do you think about that?
So the downside here is that we have to compile it implicitly, and this adds an overhead, obviously.
Yep.
And also, we are not able to leverage such features as, for example, snap start, for example.
At least as of now. In case if the features
Yes,
are introduced, and yep, I feel that they might be adopted somehow. I can't
maybe.
say for sure, so yep, still have some doubts. But that's at least interesting, and this might be the area where this might be applicable in production, kind of at least.
Probably.
Yep. And I see that there is a comment about the vector API. Yep. Vector API, it's what we are used with Apache Airflow several years ago. Nice to have it with JDK 24. So basically, the Vector API itself has been released earlier. I can say for sure the exact version, but this is more about the adjustments and improvements. Am I correct?
Yes, so it's evolving. It's still evolving.
So, yep, looking forward to seeing whether this might become the good replacement to Apache Arrow somehow. Yep. So there was also a short discussion regarding the previous section. So guys still have some concerns about whether all of that necessity to learn some new features and all of that stuff worth in terms of gatherers worth like the benefits in terms of performance and all of that. So there was a discussion in the chat. And just a side note from it about calculating sliding window of averages, as it was demonstrated, this is also at least easy way to do a parallel friendly and concise code with JDK 24. Yep. And actually, I see the the Kotlin developers in the chat. Many things we use in Kotlin for years that start appearing in Java. Yep, trying to gather all the best from other JVM-based languages. So, yep, more or less that's it about the questions, and we're ready to go further.
Yes. So let's wrap up with some more performance, more internals related upgrades. And let's warm up with a list of small changes, including some virtual thread improvements. The initial release of virtual threads came with some limitations, and one of the major ones was about how it interoperates with synchronization. Previously, if you used a synchronized code block in a virtual thread, the virtual thread would actually block the underlying platform thread, which is not a good thing. But now it's possible to safely use synchronized code blocks, which is very good for legacy libraries, legacy frameworks, which are not able to update that as fast as JDK does. But nevertheless, the issue with native code invocations is still here, so virtual threads will continue blocking the underlying platform threads with native calls. Beware of that. Also, we have the removal of non-generational mode for ZGC because the generational mode is basically a lot better and has proven itself in production environments pretty well. Next, we have an improvement in G1 garbage collector, and it's about the way how it interacts with just-in-time compilers. And now it's able to perform a little bit better in that respect. Next, we have a GEP related to the improvement of startup times. And this is about class loading and linking. So as we all know, JVM is pretty heavy on what it does initially before it's able to warm up, apply just-in-time optimizations, etc. So before that, JVM has to scan class path, module path, potentially extract a lot of data, parse bytecode files, load them, verify them, link them, etc. But this feature, namely ahead of time class loading and linking, is able to capture a snapshot of what is obtained after doing all that, and to reuse these data as an archive for subsequent startups of the JVM, of the application itself. So, for example, it's possible to capture such an archive in a test environment and then reuse that in a production environment, which is very good, for example, for quickly scaling microservices. And basically, the workflow for that is comprised of 3 steps. The first step is to capture the ahead of time config. And that's about letting the JVM know which classes it needs to pre-process. So in this case, we provide a couple of flags and run the Java application with some, for example, tests, end-to-end tests. Then we got a configuration file as an output, and we feed that file as an input to the second step, which is about building the actual archive AOT cache. And in this mode, Java will just start, load the classes, and shut down immediately, producing the archive as its output. And then we are able to take this archive/cache as another build artifact, for example, and reuse it in later deployments. But there are some pitfalls. So first of all, it's necessary to carefully consider what load and what environment you use for capturing the archives. And it's recommended to use some sort, for example, of end-to-end tests to simulate production-like workloads. Also, it's dangerous to, not dangerous, but inefficient to do these extra steps, for example, on a build machine during unit tests or integration tests, because the archive will capture all the classes that JVM loads, including test frameworks and tools, which will bloat your archive size for sure. And also, probably in the future, the JDK devs will alleviate those limitations, but for now, it is what it is. And as for the pitfalls, beware that it's necessary to use the same JVM, the same GC settings, the same OS, and the same CPU architecture when you do all the 3 steps. Otherwise, your application will just throw an error and ignore your AOT cache. Then it's necessary to align the class path and module path during those steps. So on the third step, namely the production launch, it's necessary to have a class path which is at least a superset of what we used on the first 2 steps. Otherwise, JVM will not able to load some data and will ignore your AOT cache again. Also, it's impossible to use any agents or instrumentations which manipulates bytecode. Yeah, this is pretty obvious because the data is pretty low level and it heavily depends on the source code of classes. And finally, unfortunately, it's not possible to use ZGC for now with this feature. Hopefully, those limitations will be improved or removed completely in subsequent JDK releases. And as you might have noticed, AOT linking is pretty similar to what CDS does, and CDS is class data sharing. And yes, it's basically an extension of CDS. It does what CDS provides already, and on top of that, it does the job of capturing the data provided by the linking steps, which, and according to some early tests, the boost might be as high as 20 to 40%. But of course, it heavily depends on what the application does during its startup. So for example, if your application does a lot of reflection jobs and, for example, warms up some caches, the performance gains won't be as striking as you might want. The next GP is about another optimization, and now it's about memory consumption. And the reason for that is that prior to JDK 24, JVM almost always required extra bits per every object in your heap, which might add a pretty significant overhead in case you work with lots of objects, so thousands, millions, etc. Some pre-existing options allow to reduce this number somehow, but just a little bit, to be honest. And if we look at the original layout of object headers, we have 64 bits dedicated to hash code of the object, now then followed by some garbage collection related data flags, and finally followed by some JVM specific flags which might be specific for different vendors like Oracle, Zool, etc. Then we have the class pointer itself, which comprises of also 64 bits. And only then we have object fields. In practice, it was proven that those numbers might be somewhat reduced, and this is what this GP is about. It's still experimental, so you have to supply the unlock experimental VM options flag, and only then you will be able to use the compact headers as well. But hopefully, as some testing goes on and feedback gathered, we will be able to see this feature maybe even enabled by default in subsequent JDK releases. And what it does, it reduces this extra overhead twice, down to just 64 bits. So it reduces both the hash code, the GC flags, and the class pointer itself. And we also see that there is a place for the so well-known Valhalla project, which we will hopefully see in nearest releases as well. And as preliminary benchmarks show, the gains might lead to up to 20% of heap reduction and also reduces CPU strain, especially in resource-limited environments like serverless functions. So this is according to AWS with their Pareto distribution of JDK. And there are, of course, a couple of limitations. So first of all, it's impossible to use extra large heaps, but I believe 8 terabytes is more than enough for most applications. And finally, we are able to have only 1 million of classes, which is a huge number as well, I would say. Next, we have another garbage collection improvement, and this time this is an experimental mode for Shenandoah, which tries to repeat the success of generational approach in ZGC. So just to recap, on the high level, Shenandoah is a low-pulse garbage collector. Currently, it doesn't use any generations at all and is able to conduct most of its activities completely in parallel with application threads. And behind the scenes, it tries to work just in parallel. Then, if some metrics get worse, it tries to throttle application threads just a little bit. Then, if GC failures occur, regardless of those efforts, the stop the world pause happens. And in the worst case, when the heap is heavily fragmented, the GC has to do some heavy work. But those two last cases should be pretty rare, except for some specific situations, like, for example, when the application allocates a lot of small objects very quickly. So in those cases, those degradations might happen. And the generational mode tries to solve this problem by introducing generations, just like ZGC has already done in the past. So to unlock this feature, you have to use Shenandoah, obviously. Then you have to unlock experimental features and then specify the desired garbage collection mode to generational. So regarding those JVM-related upgrades, we'll have a quiz after this presentation because obviously we wanted to include some more details, some more benchmarks on those topics, but our presentation would grow just unmanageable in this case. So please visit the quiz and let us know whether we should prepare another presentation on those topics exclusively. But besides that, you might find some useful articles on all the materials covered in this presentation and the sample source code on GitHub as well, as promised. And now let's wrap up with final questions. Tatiana?
Yep, thank you. Thank you very much for this fantastic effort. And by the way, guys, I think that this is the right time for us to share the survey, the quiz, which Johan has mentioned. So the link in the chat can be found on both Weir community platform and YouTube. And I think that we could also share some results and QR codes. So let's switch the presentation mode if possible. Until that, I think that, yep, here it is. So please feel free to use this form to vote for the topics which are interesting for you, as well as like the next screen of this survey is about your own topics which you would like to know more about, possibly. So yep, I see that basically there are some questions in the chat. The first one, wait a minute, generational GCs were from the day one, the young and old generation. This is not something new. Zero post DS is a feature. So I think that this is more about how the Shenandoah itself was built. Am I correct?
Yes, actually, the hope was that a region-based approach would cover all the needs of garbage collection in modern applications. But as production experience showed with ZGC first and then with Shenandoah, there are gaps that cannot be efficiently covered with a region-based approach, and generations has to be returned to those garbage collection algorithms. And basically, the initial version of ZGC, as well as the current version, the current production-ready version of Shenandoah, does not use any generations at all, actually, just for your information.
So yeah, this is exactly the attempt of one particular, let's say, one particular garbage collector to actually be generationless, which in fact was quite an experience, and possibly the generation full, let's say, version might work better, but let's see. Actually, this is, I think, still under the question, which drawbacks we might have while trying to adapt generations within Shenandoah. And yep,
So just to clarify, as I understand this question is that with generations, you are able to handle more efficiently, more predictable workloads, and region-based ones are better suited for unpredictable workloads. And in the real world, you have to use both, actually. So this is what it's about.
Yep. In the chat, there is clarification. So it looks like there was a move from generational to non-generational, and now we're going back. Yep, exactly. This is exactly it. So, yep, thank you very much, by the way, for the ones who have already voted. We have quite a significant number of responses, but we're looking forward for more. Actually, this form will be available for you after the meeting as well. So please feel free to vote, to share your opinion and to share your ideas, since, as I already mentioned, the form also allows you to post some additional topics which you would like to hear about. By the way, one more question. Is there any new features about desktop graphical user interface development in JDK 24? So have you seen something about the... So possibly this also might be an interesting area to dig into, but I can say for sure I've also I haven't at least seen any like significant changes in terms of graphical user interface libraries. So yep. I see that guys have posted a lot of thanks messages already. Yep, thanks for you to staying with us all that time. Yep. So there was also a correct mention in the chat that in general regions were first introduced in G1 GC, which is current default one. Yep, absolutely correct. And also my special thanks for the guys who have had absolutely fantastic conversation on the community platform regarding the different languages. So let me briefly share it with you as well. So this is not about the questions, but still, I would like to remind that one of the topics was that the best features from Kotlin have come to Java, and then there was a post that I have told for a while. I believe we will probably stop using Kotlin in future because Java will cover all its best features. And the next comment was, and then we'll stop using Java since Python will have the best from all the worlds. Yep, so that's quite interesting. And the final response.
Python is getting new features like just-in-time compilation as well. So quite competition.
Yep. And there was also discussion about some that Python mostly is C Python based, etc., and also about all the other projects will switch to Kotlin, will not wait until Java will adapt all the features. So yep, guys, you're absolutely fantastic. Thank you for this interesting conversation. And I see also an interesting post. Looking forward for more sessions which include AI and post-quantum crypto support. So that's kind of interesting. Possibly we might consider this as some topics which would be covered, I don't know, in some further workshops or presentations. And well, by the way, guys,
just a small spoiler. Actually, I considered benchmarking the new garbage collection algorithms on JLlama. So this is about AI exactly. So probably this topic is quite in demand.
Yep. Actually, there is one more question where to get repo and check your code. So the presentation with all the links and separately the link to the code base will be attached to the description on the YouTube platform, as well as to the talk on the Weir community platform somewhere after the talk. So we'll try to do this as fast as possible, but don't hesitate to visit the page later and you will be able to actually check the code and test it yourself. By the way, guys, in
Sorry, I would
case
like
if
to insert one word of warning regarding the source code. So basically, this is a Gradle-based project, and Gradle unfortunately didn't support JDK 24 at the moment of this presentation. So there are instructions on how to configure your build so that it works in the README file. Please read it.
Yep, the Java version is so fresh. So as far as I remember, you've met even more issues, but they have been just resolved like a week before the presentation or so. So yep, guys, if you're watching us as a recording, it's possible that the appropriate patches have already been released. Yep. So what was a problem to use Maven? Actually, can't say for sure whether Maven has all this.
It's a matter of preference, just.
Yep, still does make sense because this is like the own code and example. By the way, guys, you have all the source code in place. You can just migrate it from Gradle to Maven if you prefer. So your fork, your rules. And let me remind you that in case if you like our event and if you would like to share your words of appreciation with our speaker, please don't hesitate to visit the We're Community Platform Talk page, rate the talk, rate the speaker, and use the thank you button to actually share your thoughts and badge with the speaker. So we have quite a lot of answers to the form, and actually I think that more or less that's it in terms of questions. So guys, giving you just a final moment, and yeah, the repo link will be provided. Thank you one more time for reminding about that. It will be shared on the We're Community Platform Talk page below the talk in the description section, as well as in the description of the YouTube video after the session is ended. So please don't hesitate to revisit the page and possibly even rewatch the recording in case if you need some more details about how exactly to test something and you need just to remind them from the presentation. So yep, more or less that's it. I think we don't have any questions, so we can save some time. Thank you, Jochen, for the fantastic presentation. I hope that we will have continuation of this series with some topics which are interesting for our audience. And guys, in case if you're interested in becoming a speaker for our workshops, also please don't hesitate to contact our team of JCAF community. We'll be happy to see new speakers on our stage. So thank you very much and have a good day.